All right, thanks very much, Ryan, and thanks to all the organizers. I feel like it's been very smooth coming into this meeting, and hopefully it'll be a wonderful meeting all the way through. So I was invited to talk about the high spectral resolution. I will include some data from SOFIA as well as from the ground. So I guess I'm cheating a little bit. But that's a lot of the work that I do right now. And I do want to mention some of my instrumental collaborators, John Lacey, Dan Jaffe, UT Austin, were mentors for me. Tommy Greathouse and Curtis DeWitt, Ed Montiel have all been working with me for a lot of years, either on the ground or in SOFIA, and have helped make things a little more enjoyable at 3 in the morning, a little less stressful. And then also Rohini Giles and Maisie Rashman are, well, Maisie's newer to the collaboration. Rohini is newer to me, but I want to acknowledge both of them as well. And I'll point out that the slides for my title slide in the background, you can see a 32-pound piece of aluminum, 1 meter long, which is the XE's reflection grating, diamond machined so that it operates well, down to about 4 microns, I think. So I'm going to start with some definitions. For the purposes of this talk, our resolution is resolving power 20,000 or more. The spectra to the right there from Urschel, John Lacey's previous instrument back in the late 80s, early 90s, is at R of 10,000, so it wouldn't qualify under my definition, even though Urschel was the first instrument to see interstellar acetylene, interstellar methane in, I believe it's one of the advantages of the mid-IR, are these symmetric molecules, which do not have rotational transitions, can be seen by their rho vibrational transitions. Another thing, I'm going to call infrared from around 5 microns to 28 microns for my talk. Basically, this is the wavelength of where arsenic doped silicon detectors, like are featured in MIRI on JWST, where they're sensitive. So I'm not going to be talking about too much about the excellent work done 3 to 5 microns by some of the ground-based spectrographs. I'll be naming them later. The atmosphere that I'm concerned with, well, you can see some of the range in the lower plot, where I've got an atmospheric model of Mauna Kea in kind of the purplish color, and SOFIA in green in the transmission. And you can see that from the ground, of course, there's some places that are really quite good. At high spectral resolution, you can get around the little sawtooths. You don't care about them too much, so long as you have a decent Doppler shift. And from SOFIA, particularly in the 5 to 8 micron region, where water and methane are big absorbers, you're able again to work around the sawtooths. And I guess the other thing that, looking at the atmosphere, I want to bring up is, normally high spectral resolution, you use a comparison object, so that way you can correct for the atmosphere. And I think that's going to be less important in the future. Atmospheric modeling is getting better and better, and that will not only save observing time and let us concentrate on the targets, but it end up making the observations just so much easier. All right, the final thing for this first slide, I'm afraid I'm going to be using wave numbers and wavelength interchangeably. My postdocs have gotten used to it. after frustrating weeks, months, whatever. But keep in mind, it's an inverse relationship. So if you're at 500 inverse centimeters, that's 20 microns. 1,000 inverse centimeters is 10 microns. It's not too important, but I thought I'd bring it up. So I just felt like I should list some of the current high resolution IR spectrographs. The blue are the short wavelength ones. So they come out to 5 microns. And the red are the high spectral resolution mid-infrared, 5 microns and beyond. And in comparison, I felt it important to compare us with the space spectrographs that have gone up. ISO at an R of 2000, Spitzer IRS with its high resolution being 600 resolving power. And then MIRI should have about 3000. And to bring that home, those numbers home, I thought I'd do a little comparison. So I created a simple absorption spectrum of HCN and acetylene. This is all out about 13 microns. And in each case, I convolved the spectrum or resampled the spectrum to the appropriate resolving powers and added noise. So it's a signal to noise of 100. And you can see that, yes, the lower resolving power can pick out where the lines are piling up. So the high equivalent width Q branches for these species. But there's some other things I want to point out. If you'll notice at about in the green, I've drawn a line where the base of the Q branch is. This is a 20% absorption feature when presented at an R of 3000. I'll come back to that a little later. The orange lines, the vertical lines, show you a typical XE's coverage. On TEXES is a little bit smaller. VZIR would be a bit smaller still. And so in these high spectral resolution ground-based instruments right now, we're certainly not getting a whole lot of the spectrum at one time. There are modes that we can use, and I think XE's is the most successful in this, to try and look at a bright point source with large wavelength coverage. You actually can get about 40 wave numbers. So more than half of this slide in a single setting. Okay, so now I'm going to zoom in and just looking at the 10,000 and the 100,000 spectra. And if you look at the lines and the black lines, you can even start to see the artificial line profile I put in there. It's not quite a Gaussian. It's a bit of a half triangular. I want to point out again, remind you, at R of 3000, the depth of the acetylene Q branch was 20%, when actually these lines are going 35% or so deep in this slide. So that's one of the advantages of high spectral resolution, is you can get the full sensitivity if you match the actual line width. Oh, and the other thing, if you know about acetylene, it's got statistical weights. So you start to see the 3-to-1 odd even effect of the statistical weights in the molecule here. All right. Ground-based observatory is not easy though. And so this is again the R of 100,000 absorption slide. And below it, I've pulled out the atmospheric transmission from Mauna Kea in red and from Sophia in blue. So there are some wavelengths from the ground you just won't be able to do. You can observe even when transmission is quite low, and you can correct for it. as I say, with a telluric calibrator or increasingly with atmospheric models. Okay, I wanted to present a little bit of the history. So prior to TEXIS in 2000, if you wanted to find high spectral resolution in the mid-infrared, you used an FTS. And this is a paper or a plot from a paper in 1986 by Jennings, where they used the Kit peak 4 meter with a Fourier transform spectrograph, spectrometer. And they used a special predisperser and bandpass filter to eliminate noise coming in from other wavelengths, which is a feature of Fourier transform spectrometers. So in the plot, if you look out towards where it's near zero, that's pure noise. That's just what's coming outside the bandpass filter. The resolving power is 50K, 50,000. They're looking at two really bright stars, Alpha Tau, Alpha Ori, and they're looking at it with a 4-meter telescope for hours and hours. In 2000, in October, TEXIS got to the IRTF, 3-meter telescope, fantastic site, Mauna Kea. And we looked at Alpha Tau. Mind you, this was a really cruddy observing run. We had 8 nights on the telescope, and I think we had 8 hours total, day or night, when we could actually open the dome. But in that time, we did manage to spend about 4 minutes on Alpha Tau in that same wavelength setting, and you can see the spectrum there. And it's just fantastic. I mean, the comparison it's wonderful. We had more spectral coverage than they did with the FTS, and it really made us happy and looking forward to when we actually got good weather on Mauna Kea. I want to point out, most all those features in the Alpha Tau spectrum are water. And if you go back through earlier infrared, when they used telluric calibrators, frequently they used K and M stars. All those stars have water in their photosphere, so that makes them a little harder to use as comparison objects. Okay, so with TEXIS, eventually we got onto Gemini, where we usually run from the IRTF, and the instrument has not moved from the summit of Mauna Kea in 20-some years now. But there was one observing run on Gemini, and we were looking for HCN in a disk source, RW or IG. A nice feature that we had with TEXIS is that we could do pipeline reductions in near real time. So you take a file, you copy it over, and you pipeline it while you're taking the next file. And that way you've got an idea of what you're seeing. And using this, we could see, well, the HCN we wanted wasn't coming in, but there's this other line. There's something there. Keep integrating, guys. Go for it. So we used our atmospheric model, and we figured out the line that was coming in was a water line. That's very surprising. Water is not easy to see from the ground. But that's what we're pretty certain, or that's what we knew it was, and later analysis bore it out. Claudia Nez presented a poster in 2007 that showed this nice figure of a simple sort of LTE disk model that kind of matches the line profile and has the emission coming from around 1 AU or a little bit less. I do want to point out here as well, I put in the JWST resolution element for MIRI, or an R of 3000, and you can see that all that line profile information disappears. All right, so once you find water in one source, you're going to go looking for it in lots of other sources. And so here's a collection from a paper by Colette Salick, 2019, where she was showing one single setting with taxis where there are several water lines, 3 water lines that come in at the same time. And it's a variety of sources. The paper includes data from Michel and some results from V0 as well. So it's not just taxis that can look for water from the ground at these wavelengths. You are looking at excited states. That's what lets them come through the ground, through the atmosphere. So the excitation temperatures of these transitions is 4,000 to 6,000 K. Using the data, the results, Colette derived temperatures for these different sources, 400 to 1,000 Kelvin. You'll notice some line profile variations. Some are quite broad, up to 100 kilometers a second, and some feature at least a narrow component as narrow as 10 to 15 kilometers a second. And those narrow line cores all sort of match what's seen in CO. The last thing I want to point out is the faintest source here from Gemini was about 0.6 Janskys in the continuum. And there are other sources that beyond just what's in this list that you can do at that level. So there's more science to be gotten here. All right, so as well as looking in for other sources with water, you might look for other molecules and disks. Joan Najita in 2018 was looking at acetylene and HCN and water from 2 sources, AS205 North and DR Tau. In the plots you can see below on the left-hand side, it's 2 HCN lines averaged together in black with 1 acetylene line from the same setting in the blue, and you can see they look very similar. So then if you increase the signal noise by combining all 3 organic lines and compare it with a water line, you can see again, the line profile looks essentially the same. So kinematically, you can say that whatever gas is emitting in these species, it's the same gas in terms of its velocity. So as I say, from the ground, it's very hard to do water unless you have these high excitation lines. So if you're looking for water absorption, you're more likely going to be getting, well, it's harder to probe the low-lying states. With XEs on Sophia and a bit of a Doppler shift, you have access to essentially the entire water ladder, including down to the ground state line. We're seeing water absorption out of the ground state, the 0, 0, 0 line. And this slide comes from a paper by Nick Indriolo in 2020, where he was looking at, well, the paper actually includes a lot of CRIRES and TEXIS data as well, comparing water across multiple wavelengths, 3 to 12 microns. And one, I think, well, not surprising result, but nice to have it shown, is that a single absorbing slab isothermal doesn't work. It really doesn't work, because the strong lines in Nick's analysis in these data all showed up as weaker than they should have been for an isothermal slab. You can get around that by including dust mixed in with the gas, and dust is serving as your background. And so in the strong lines, you're not seeing as much of the column because you're running into where the dust is, or you're running into dust mixed with gas in the object. And naturally, no one, I think, ever expected to have a pure dust shell around a hot star like AFGL2136, and then a gas layer outside it. So it was,
5 minutes.
I thought it was very nice to demonstrate this. Okay, thank you. The other thing that comes with the line profiles here and combining the infrared with ALMA. ALMA, you see the continuum emission down in the lower right, and AFGL 2136 has a disk, which has some enhancements within it. And if you make assumptions about what might be going on with velocity, you can find the components in the water absorption match where you would expect the velocities that you'd expect with these density enhancements within the disk. So it's a nice way of locating material spectroscopically beyond just what you could do, even imaging this in the mid-infrared. And JWST, of course, won't have the velocity detail. All right, JWST will have great sensitivity, just due to the fact that it's a cold space telescope and doesn't have to deal with the atmosphere. I'm going to say that better than for continuum, JWST is going to be thousands of times better than TEXI's on an 8 meter. I want to go on, talk about ground-based. So I've listed EELT METIS and GMT NIRS. GMT NIRS will have higher spectral resolution in the 3 to 5 micron region. METIS is an IFU. GMT NIRS will be optimized for wavelength coverage. TMT MICHI will include R of 100,000 at least out into the 13 micron region. So the wavelengths I've been talking about. And here you get from a 30 meter, you get to a chances of actually directly relating to JWST in some cases, I think. So if you had an unresolved line, yes, JWST still gives you better signal to noise, but it's less than a factor of 10 if the line were unresolved by MICHI. Okay, I'm going to move on. Ryan, I'm going to say that I've got a problem that my VPN is canceling out. I'll try and deal with this very quickly because it won't let me otherwise. So finally, what about a high spectral resolution instrument in space? Wouldn't that be nice? Have to decide what the best wavelength range is. I would say you want it to be where there are a lot of ground-based interference. You want it to be something where you benefit from having a cold space telescope. And the other problem with getting high spectral resolution into space has to do with the grating size. So in theory, the resolving power is the optical path difference from the first groove to the last groove in waves. And you get an extra factor of 2. I think I actually wrote that wrong. It should be multiplied by 2.
1 minute.
And so, okay. And you can do this using immersion gratings. And there are instruments like iShell, iGrins that currently use silicon immersion gratings. GMT NIRS and METIS will use silicon immersion gratings for 3 to 5. And so inside the crystal, you're effectively have reduced your wavelength, so you've increased your spectral resolution. Now, I would say for space, you actually want germanium because the N is 4, so that means that the beam feeding the grating is 16 times smaller in area, and you get to reduce the instrument, the mass and volume because of that. And germanium transmits well-ish from 2 to 18. but it transmits very well from 3 to 8. So I'm working on a project where we're trying to build a prototype 3 to 8 micron R of 25,000 to 40,000 single shot 2-arm that gives you that whole wavelength region. And hopefully we'll take it on to a ground-based telescope and get it ready for eventually going to space. Sorry about the hurried ending, but I'll stop there.
All right, thank you for the great talk, Matt. So if anyone has any questions, feel free to raise your hand in Zoom. Let's see, so Matt, I did have a question about the Indriolo et al. 2020 results on the dust or the presence of dust mixed with gas. So I was curious why that was surprising. I guess it wouldn't seem too surprising to me.
I guess
like you have.
No, I must have misspoken. I don't think it was surprising. It's something that everyone expects, but no one had done the analysis. No one had really shown it. And so that's the new thing. It's just easier to do a slab model, right? Rather than the radiative transfer. And so much of the absorption work that has been done in the mid-infrared used a slab in front of a background source. And Indriolo et al. Went to that trouble to show that really that's not what you're getting. And I should comment, there's also Barr et al. Used some of the same sources, and Andrew Barr's got a paper out on a lot of the organic molecules, and his PhD dissertation has more stuff, and there's another paper in the works. But he went to more trouble than just the simple slab, because as we've improved the data and gotten more lines to analyze, the simple slab just doesn't work.
I see. Yeah, thanks for the answer. Okay, and on Slack, we have a question from Pat Roche. So they're asking, is a resolving power of 100,000 optimum? Half the resolution would give twice the wavelength coverage and higher signal to noise per pixel.
Yeah, that's a question. I would argue that it's very rare to find some line that's 3 kilometers a second. And there are cases where that does happen, but no, I think that Pat's got a really good point. R of 50,000, also you can do some fantastic science. We're greedy. Why can't we have both the resolving power and the wavelength coverage? And if we get up in space with a cold space telescope, why not get all the signal to noise as well?